3D equilibrium. In these cases, we are going to have 3 forces to balance, 3 moments to balance, so it comes down to 6 equations, 6 unknowns. And like the 2D case, when we're drawing our free body diagram, we're going to have to really pay attention to how things are connected to the walls, recognize features like if it's a cable, the force is in the same direction as the cable. So let's go through some of the different three-dimensional connections and how to draw the free body diagrams, because that's going to be the first step for all of these. For three-dimensional connections, again, you're going to think about which way that support can move. So for these guys, if it can roll around on the floor or there's no friction, the only way it cannot move is through the floor. It can't move that way because there's a force pushing back. So wherever it cannot move, that's where you would draw a force into your free body diagram. So again, cables are in the same direction as the force, and make sure you define what object you're drawing the forces on, because all forces happen in equal and opposite pairs. So you have to make sure you're drawing the direction correctly. So it's the force on the object you're drawing the free body diagram of. Here's rollers. If we have a situation where it can move back and forth in the x direction, if it can move in that direction, there's no force stopping the motion in that direction, but it can't move through the floor. So in this case, there would be a force in the y direction, and it's not going to jump off of that rail. Or if it's a rough surface, it doesn't want to roll in the z direction. So there would be a force opposing motion in the z direction from the friction or from that rail, and then the floor has that normal force on it. Okay, ball and socket. These guys cannot move off that spot or a rough surface, so there's going to be friction in all the directions along the floor. So you have the normal force coming up in the y direction again, and you have x and z forces because it can't move, but in this case there's no resisting moment, so it can rotate. There's resistance to sliding around in the x and the z direction on the floor in this case. Some different connectors. So here's the worst case scenario, a fixed support. It can't move in the XYZ direction, and it also is unable to rotate in those directions. So this one little support, you would have 6 unknowns here. You would have to solve for all 3 moments and all 3 forces because it can fight all of those different motions. So that's kind of the worst case scenario. Here's this guy, so it can't move in the XYZ direction, and this one it can not rotate around the x-axis, so it's resisting that rotational motion as well. Read the problem statements very carefully on this. So they will tell you if it can slide around in the radial direction or if it is stuck in place so that it cannot move in any of those directions, and then look at which way it can rotate and which way it is unable to rotate. And that's going to define how you draw the reaction of the supports at those free body diagrams. So pay attention to which way it can't move, and that will whittle away your unknowns so that you can actually solve for it. So again, we're looking for 6 equations. You can only solve for 6 unknowns. If you find yourself drawing in more than 6 unknowns on one of these problems, check your supports again. There's probably one direction that you drew in an extra force that you can get rid of. Here's an equilibrium example for a 3-dimensional problem. What we have is a 10-foot long pole sticking out of the wall, and over at the end of this thing we have an 840-pound force hanging off the end of it. Determine the tension in each cable and the reaction at the ball and socket joint at A. Ball and socket joint. This is the kind of connection that it's not going to move, so we're going to have X, Y, and Z forces unknown at that point A, it can rotate around A. So ball and socket joint can rotate, so we will not have moments fighting it back. So A will have three unknowns, AX, AY, AZ, the forces in those three directions. We also don't know the tensions. So this case has 5 unknowns, 2 tensions, 3 reactions at A, and for three-dimensional problems we have 6 equilibrium equations to solve for it. First step in any of these problems, draw a good free body diagram and really draw this thing. If you want, you can use your snipping tool. Just say new, drag and drop, and your snipping tool has markers on it, okay? So go ahead and use that to grab that picture. So free body diagram, we want to pick one piece of it. The pole is where all of the forces come together, so we're going to draw the forces acting on that pole with respect to the pole. If we start drawing forces on here, we have the 840-pound force hanging off the end. That's already drawn in for us. The tensions are pulling up from point B, and we can call this tension BE, and this one we'll call tension BD. And we also have a bunch of forces at A. So there is some force in the X direction at A. We have some force in the Z direction at A. And we have a force in the Y direction. If you don't know the direction of the forces, draw them in the positive direction, and then when you crank through the algebra, you'll see where some of them might go negative, and you just have to know that, I have to run over and change around what my vectors were for that. So default, draw them in the positive direction, and if the signs have to flip around as you're solving the algebra, then so be it. Okay, so that's how you draw a free body diagram. Isolate a chunk of it. Sometimes it helps to actually draw a line around the piece that you're isolating, and then look at what crosses that line. So my 840-pound force crosses that line. We know we have to draw a force there. The tensions, we are chopping through those tensions in order to isolate this piece, so we're placing anything we cut with a force. And then we have to also pull this off of the wall here. So instead of having the wall connected to it, we now have a bunch of forces over here connected to it. So we have forces in the XYZ direction at the point A. We have the 2 tensions and the 840 pounds hanging off the end. Okay, so take your time and draw a really good free body diagram on this. That's super important. The next step, we're going to break everything into XYZ components. Now, we do not know the tension in these cables yet, but even though we don't know the tensions yet, we can still break them into XYZ component. We can look at the unit vectors. So let's just do what you can, get as far as you can, and the information you don't have, write it in as a variable, leave it blank. But the first step is just fill in as much information as you possibly can. Let's start with cable BD. And again, we're going from the pole. The free body diagram we drew was from with the respect to the pole. So we're going from the pole, and the force is pulling up, back and up. So here's our distances, and you're going to have to just look at the figure for those distances. So dx, we're going in the negative direction. See how that's going back from the tail to the tip of the arrow. Y is coming up 7 feet. See where that 7 feet is. DZ is forward 6 feet. And then the overall length of that cable, the overall distance between B and D, we're going to just say equals square root. And that's going to be dx squared plus dy squared plus dz squared. Okay, so there's the overall length of the cable. Now we have to turn those lengths into a unit vector, and all we're doing here is just seeing what fraction of the length is in the x direction. I'm going to add dollar signs with F4 so I can copy this equation down. So there we go. Here's the fraction in the y direction, and the fraction in the z direction. See how the cell I added dollar signs to, those keep the red cell constant, whereas that initial cell that does not have dollar signs, when I copy the equation down, it updates that. So this is B42 and this is B43, so it just keeps moving that up as you copy it. Okay, so there's our unit vector. We can say Control C, Control V, and copy over that square root equation. Make sure that our unit vector is adding up to 1 like it's supposed to. We still don't know the force over here, so we will come back and fill that in later, but at least we know the unit vector. So there's the first tension, that first cable. Do the same thing for this other cable over here. So here we go. We've got cable from B to E, and I'm seeing some similarities here. So we're going back the same distance in both of these cases. So dx is -6 for both of them. Both of them come up to the same height, so we have +7 for both of them. And it looks like the only difference between these two cables is what's happening in the z direction. One is forward, the other one is negative. Okay, Control C, Control V. They have the same length on each of those guys. I'm just going to copy that equation in. Control V as I have it. Okay, so here's the unit vector for the x direction, dx divided by d. F4 holds a constant. Copy that equation down. So those cables are pretty similar. If you see symmetry in something, what does that mean about the magnitude of them? If they're symmetrical, the magnitude's probably the same. And they're going to have to tug equally in the z direction. If they didn't tug equally in the z direction, that thing would be rotating around point A. So they kind of have to be symmetrical. So notice lines of symmetry on this. Okay, our force table. So eventually we're going to need to know the x, y, z components of all of these forces. Now we don't know the tensions yet, but we can at least fill in this 840. So the 840 is straight down in the j direction. Nothing in the x, -840j, nothing in the z. And we also have forces to fill in for both of those tensions, and we have x, y, z for our A force. Usually in these problems, you're not going to start with all of your force equations. You have more unknowns in your force equation than in your moment equation. We're going to start our algebra and our solving with the moments. And the reason we start with the moments is because we can take the moment around point A, and that eliminates all of the unknowns at point A. So there's no A forces in our moment equation. That makes our moment equations easier to solve, and so usually you're going to start with the moments for this one. Okay, so we're going to take the moment around point A. That eliminates all the unknowns from AX, AY, AZ are not going into this moment equation. And we've got 3 cross products to crank through here. Okay, so we have from A to the 840 pounds at the end, from A to the tensions at B. Let's go ahead and fill in the position vectors here. So we're going from A, from the axis of rotation to where the force is applied. And let me know if that doesn't make sense, why we're taking the moment around A. This is taking the moment around the right spot is going to be what simplifies these problems for you. Okay, so if we have remember force goes on the bottom of these cross products. So there's our weight hanging off the end of it in the negative j direction. And then here is our length. We're just walking down this pole, and that's going to be +10 for this guy. 6 + 4, 10, from the origin to where the force is applied. These next two, from the origin to where the force is, they're going to be 6. 0, 0. Control C, Control V. It's the same distance for both of these tensions. And if you recognize the symmetry, you can see it's the same tension in both of those cables. So what we can do is pull the tension out of the cross product and just put our unit vectors in here. Okay, so I'm going to grab our unit vectors, and then it's multiplied by tension, by tension, by tension, x, y, z. So all we have to do is just say equals, here's the x component, equals, there's the y component, there's the k component. So 6/11, 7th 11th, 6/11. And here's the other one. Again, 6/11, 7/11, and 6/11. And the only difference there was those negative signs. Okay, so we have, all we have for our unknowns for our moment cross products is the tension in those cables. Okay, so that really simplifies life, and we're just going to multiply each one of these guys by that tension. Okay, so here's our cross products. I is J times J minus K times J. And here's, remember, J goes opposite. We're going to start in the upper right-hand corner. It's a bunch of zeros here. But I'm just going to plug this in anyway. So there's our J cross product. Here's our K. So K is upper right times this guy minus 0 times 0. Okay, so all we have generated from the 840 pound, it is rotating. Let me grab this. So this force is going to rotate it around the K axis. See how he's going to rotate it around here? And use your right-hand rule. So for the right-hand rule, the vector is in the negative K direction. See how if you wrap your fingers around here, your thumb is pointing backwards in this case. So that's your K moment here. It's describing the axis it's rotating around. This force is rotating it around the K axis, and that's going to be a negative moment because of that right-hand rule. Okay, so there's our first moment. Once I have these moment equations in, I've got this set up so I can say Control C, Control V, Control V. There you go. There's the moments for each of those guys, because I didn't add dollar signs, so it's going to just move those cells over right to where I need them to be. Now, for these guys, these are all multiplied by T. Okay, so I've got a bunch of T's in here that we need to pay attention to. But for all of these, there's only one unknown. Okay, so you can write this out, write your calculations out on a piece of scratch paper. Sometimes you can't do it all in Excel. You might have to get some scratch paper out to look at those algebra problems. So what do we have? In the I direction, there's nothing in the I direction. Why are all the moments 0 in the I direction? So I, that's the direction of the pole coming out here. Well, remember, moment is R cross F. R is 0 for everything in the I direction. Everything touches the x-axis. If it touches the x-axis, R is 0. There's no lever arm. There's no moment. So all of our I's end up giving 0. What's happening in the J direction? The only thing tugging it in the J direction are the cables coming up. And the cables are pulling equal and opposite around that J axis. So those cables are where we can really come and say those two tensions have to be equal. They have to equal one another out because that ball and socket joint cannot fight against a moment. So this thing will be rotating around A if those two cables are not equal and opposite. So there, from our symmetry, we can say our tensions are equal from the moments going on in the J direction. The K direction. So this is the last little bit, and it's 840 pulling down versus two tensions pulling up. See how those two tensions pulling down, those two guys are on kind of opposite teams. So we have the tensions fighting the weight to rotate around the K-axis. When we set those equal to one another, so we have the two tensions over here, and you can solve for what our tensions are. Just a little bit of algebra here. Okay, once we have our tensions, 1,100 pounds, we can go ahead and plug those back into here, and we have to break these forces into their IJK components, because eventually we still need to know all the forces at A, right? While we were solving all those moment problems, we forgot that there's all these unknowns over here at A. So the moments gave us what the tensions are. Now we have to go back to the force balance to find what A is. So here's our equilibrium equations, right? So moments solved for tension, our force balance we're going to solve for A. So here's all of our A. So and I'm going to just copy those tensions over. Okay, so 1,100. How much of it's in the XYZ direction? We're going to grab this thing, F4 holds a constant times the unit vector. So there you go. There's our tensions chunked into their IJK components. I can take that square root equation and make sure it adds together to our 1,100 so that we chunked it into XYZ components correctly. So that was the tension in BD. So it's 1,100, and here's the X and the Y and the Z components of that tension. And let's see, where did our other tension go? I hid it over here. Okay, same thing. So here's our other tension. 1,100, I'm going to hold that one constant, and we're just multiplying it by fraction in the X direction, fraction in the Y direction, fraction in the Z direction. And then I'm going to copy those XYZ components over into our force table. And then we're going to have to add all of our XYZ forces to 0. Okay, so here's our force table. We're going to add everything to 0 and solve for A. Okay, so equals sum, and everything in the X direction has to add to 0. And everything in the Y direction, and everything in the Z direction. Okay, so what is our X forces? Equals negative sum. It has to make up the difference, right? Whatever those tensions and the 840 pounds did not balance, the A has to balance that out. So you're just going to take the negative of whatever didn't balance out. And that'll make sure that each of these columns adds to 0. There's our X forces are adding to 0. Our Y forces are adding to 0. Our Z forces are also adding to 0. Let me pull that picture back over here, and let's make sure that this all makes sense for what's happening. Okay, so what do we have? We've got everything in the Z direction from the tensions are equal and opposite. They're symmetrical, so they balance one another out for the Z direction. For the Y direction, let's look at the Y direction, what's happening. We have the weight pulling down, two tensions pulling up quite a lot, and then A is actually negative. Isn't that interesting? It's like a little teeter-totter, in fact. Okay, so if you have a teeter-totter, right, we have the 840 on one side, and then we have the tensions up in the center, And what are you going to have to do so that it doesn't rotate? Well, AY has to go down. So we drew our AY force the wrong direction. We'd have to turn him around. And it turns into just a little teeter-totter. You'll see these patterns where you have up, down, up, down, little stripes where every other one is up or down. And that's what balances the moment, right? So if we took the moment around A, something rotating it up, you'd have to balance that out with something rotating down. So just make a kind of a reality check for the signs and the directions and the magnitudes of the forces at the very end to make sure that your numbers are intuitive and make sense. Okay, so that makes sense for the Y direction. The X direction, what's happening in the X direction? Well, for the X direction, we have both of the tensions are pulling forward. And so, yeah, AX better be forward. So AX is fighting against both of those tensions. So you can see both of the tensions are pulling negative, and so AX is double what those tensions are. So those numbers, they make sense. Okay, hopefully that was okay. If you are good in 2 and 3, if you know how to do unit vectors, if you know how to break forces into XYZ components, see how this is more of just what you've already done in chapters 2 and 3. So you're through the hardest part of this course. And 6 equations, 6 unknowns, it's not going to get worse than that. And it wasn't too bad, right? It wasn't too horrible. So, okay, we'll see you next time.